C6 differential equations and change of variables. Now, we're going to have to do this in our course later. And I'd like to introduce the technique early or review it for you if you've been away from your calculus courses for some time. And this kind of a problem where you have a differential equation, you're trying to find a solution, occurs so often in physics. And our course is going to involve solving differential equations, especially as we get toward the climax of our course and deriving our Sommigliano formula. Now we did this integral in the previous section. We did the integral in one of the previous sections, 0 to pi over 2, I believe it was section C2, common integrals. We did the integral x cosine of x squared dx. So what I would like to do is start with something we already know and do a problem two ways. I like to do this often, where we have one problem done the old way and then the same problem done the new way, so we can then learn a new technique. So let's look at a problem that I constructed for you so that this integral that we did in the last few chapters back is relevant here. So let's say we had the differential equation, and that means we have a derivative somewhere. So the derivative here of the function f, which we can write out specifically like this, is equal to 2x cosine x squared. Now you can see when you solve a differential equation, you have to go backwards and do the integral, and you can see that this integral is the one we're going to wind up having to do. Now, to make things a little bit simpler, I'm going to say here that at 0, the function is equal to 0, and that I'm only interested in x that is greater or equal to 0. They're the x's I'm interested in. Often you see this with the y prime, f prime of x. Differential equations often appear like this. Y prime is 2x cosine of x squared. You might see it like that. So we're going to solve this differential equation using two approaches. And method one is going to be what I did in section C2, and I'll briefly redo it for you. All right, so method one, this is the integration by substitution. All right, we already know how to do this, and let's review it. We write this down as df of x. df of x is equal to 2x cosine x squared dx. And we would like to integrate. So we're going to go here from f0 to fx on the df of x, and that's going to be equal to, on this other side, we're going to go from 0 to x of 2x cosine x squared dx. So it's almost the same integral that we did last time. There's a 2 that shows here. It's a construction of a problem. I prefer to have the 2 there so the answer is going to come out very, very nicely. And the math will be simplified. All right, so what do we do here on this side? On the left side, we simply have an integral with a differential. It's simply going to be fx evaluated at f of 0 to f of x. And then on the right side, we have, we'll write the same thing down again, 0 to x, 2x cosine of x squared dx. So we put in f of x at the top limit. Now notice that I am doing what the physicists do. There's no integration variable that we talked about in the last section. We just have x's everywhere here and not worry about it. And this becomes fx, the upper limit, minus the lower limit. And since we have the condition f of 0 is 0, this one here is gone. And then we're left with doing the integral on the right side. So in other words, f of x, the solution to our differential equation, is the integral that we did in an earlier chapter. All right, well, what did we do in that earlier chapter? Well, we used substitution, integration by substitution. In other words, we substituted for the x squared u. We let u equal x squared. And doing that, we have du is then 2x dx. And now you have to be careful that when x goes from 0 to x, what does u do? Well, when x is 0, u is 0. So for the u variable, when x is 0, u is 0. And then u is going to simply go to u, the full value. When x is x squared, u is u. All right, so we make this substitution, and when we do that, we find that here we want to have this 2x dx, we have it there. So in other words, that's going to be u. So we have f of x here is equal to, and I'm going to go here from 0 to u. I'm changing the variable, see? And then I have the cosine of x squared is cosine of u, and then 2x dx is du. The 2x dx is du. So you see, this is a nice substitution of the variable, and the integral is out really easy to do because when you integrate the cosine, you get the sine. So there's the sine of u from 0 to u, and that's going to be the sine of u minus the sine of 0, which is 0, so that's it. And then here, you remember that u is equal to x squared, so the answer is the sine of x squared. That's the solution to our differential equation, that f of x is sine of the quantity x squared. A different way, and that's method B. And method B is to transform the differential equation, the dE, by a change of variable. So the change of variable theme is reappearing, but now we're doing it at the differential equation level in the hope of getting an easier differential equation to solve. Well, in the first case, we kept the differential equation the same, and then we're faced with the integral, and then we did a variable substitution to the integral. So here we're going to pick a variable to do the change of the differential equation. A very, very important technique. So in other words, a differential equation with respect to x is going to become a differential equation with respect to u. I'm going to let the new variable be u. But what should this u be? That's a good question. Well, I'm going to let u equal x squared. Now, when you do differential equations and you solve integrals, it's the art, as I mentioned before. And here you try something and you try to see if that would work. Well, what is my original differential equation? Well, the original differential equation, let's write this down, is df of x. We write it down again here. Dx is 2x cosine of the quantity x squared. This is the original this is the original differential equation, and now I'm going to make this substitution at the differential equation level, so I have to understand how to transform d dx into some d du. So to do that, we're going to notice that du is 2x dx. And from this equation, we can write d dx is equal to, I'm going to write 1 over 2x here. In other words, the d du, basically kind of like a flipping sort of thing, where here I have d with the 2x dx, and that's going to equal d with the du, all right? Before we go on, I want to make some comments here. This is very subtle, and I want to make sure it's very clear to everyone. We start with u is x squared as an important equation, and f of x is the sign of the quantity x squared. So I have these here. U is x squared, and f of x is sign of the quantity x squared. Now, combining these, I replace the x squared with u, and now I'm very careful that I want to use a different letter than f for the function of u. But you say they're the same. Why do that? Well, here's why. If I were to use the lowercase f and put in u, well, what does any function do? Whatever you put in the argument, it does to it what it's supposed to. Well, when you put an x in, the f of x function, what it does is squares the x and then slaps on the sign. If you put the u in, it would square the u and slap on the sign. Well, that's not sign of u. You see, we get into trouble. So by picking a capital F of u for the function when it's in terms of u is the safest thing to do. Now, what about this? This can look a little scary and weird. So let's look at that. Well, u is x squared is no problem, and then du dx, the derivative, you bring the 2 down, and you have x to the 2 minus 1, 2x. Now, what I do when things look a little strange, when you might get in trouble, remember, see, these are differentials. You can't move them around easily because, see, the df dx, that's a ratio of a delta f over a delta x as the limit of delta x goes to 0. So what I'm going to do with the du dx is 2x. I'm going to replace the du dx with deltas. So now the delta x has not been taken to 0 yet, as it has over here. That's what this notation means. Now with the delta x and delta u not being 0, I can move them around at will. So I bring the delta u over on the right-hand side with absolutely no problem. Now, this df dx, I'm going to look at here. I want to transform that into a derivative with respect to u. So what I do is I take the df dx and replace it with deltas. Delta f over delta x. Now I'm going to use the equation I have above here, where the 1 over delta x is 2x over delta u. Just substitute that in down here. Now when I do that, I can look at x and get everything in terms of u because x is the square root of u. So I have the square root of u, and remember we're looking at x. So then here, with this equation, I then be very careful and change the little f to uppercase F when I want to talk about a function of u, for the reason why I explained up here. And then finally, I then take the limit as delta u goes to 0 here. And you can think of when x goes to 0, u goes to 0, and then you have this equation, which is the key equation that we'll be looking at in this lecture for substituting. So I hope that clears things up. We will continue now. So I'm trying to get rid of this d dx, so that means d dx is equal to 2x d du. I brought the 2x on the right hand side of the equation. But here I still have x, so I would like to have everything in terms of u. But u is x squared, so x is the square root of u. So this is 2 times the square root of u du. So therefore, the derivative of the function with respect to x is going to have this 2 square root of u, the derivative of the function with respect to u. But now we've got to be careful, because f of x is the one function I started with, and now I'm going to have a function with u, and that's going to be a different function. I'm going to use a capital F, all right? Because whenever you put the x in for the lowercase f, it's whatever it is, you have this, whatever you have this. But if I'm going to have the differential equation with respect to u, I want to make sure there's no misunderstanding of the use of notation. So I'm going to use capital F for the corresponding function of u that's related to the corresponding function of x. So that's what we have here for the derivative. And that would be the left-hand side. And then the right-hand side, would be 2x. And what is x? Well, x is the square root of u. We would have this. And then we would have the cosine of x squared, which is u. Now, you can see that this worked. This transforms the equation into a very, very simple one, because this is going to cancel this, and I have a very, very nice equation. D capital F of u du is equal to the cosine of u. So one approach here is to say, well, look, this function, capital F of u, has to be equal to the sine of u plus a constant. And then evaluate the constant based on what's given. Well, what was given? Remember, we said that little f of 0 is equal to 0, and x is greater equal to 0. This condition and this other condition were stated originally. So that means we can check what happens if you have capital F of u equals 0. That would be the sine of 0 plus a constant. Well, what is this capital F of 0? Well, remember that we were very careful with our notation that the little f of x is equal to the capital F of u. I was very, very careful to do that. And see here, if the u is 0, so that we're looking at this as being capital F of 0, that means since the u is equal to x squared, that means the x has to be 0. So that means we have this, and we stated that the condition was that has to be 0. So if f of 0, the lowercase f of 0 is 0, then the uppercase 1 is 0. So that means up in here, this constant is gone, because this is 0 by nature. And since we have to have this being 0, we have a 0 constant. So that means we have our function, capital F of u, equal to the sine of u. And we're still not finished, because we would like to have the answer in terms of x. But see, capital F of u, you see it was wise to call these differently, because if they were the same, we would be totally confused at this point. But here we just simply write this like that, and then get rid of the u. We come looking for where, bingo, u is x squared. So this is the sine of x squared. Now this is a very, very nice problem because what we have done is we have shown that this is the solution to our differential equation. And if we look up here, f of x is equal to sine of x squared, all right? In other words, using method 1, we found that f of x, lowercase f of x, is sine of the quantity x squared. By using the transformation variable first with the differential equation, we transform the differential equation into an equation we could solve very easily, and we've got the same result. So I always like doing this. When you learn something new, do it the old way first to really master what's going on. So we do the old way first using integration by substitution. We simply look at this integral and just do it. Let u equal x squared and do it. In the second case, we transform the differential equation, and a lot of the work was up front doing that. And then once we did that work up front, the solution popped right out. So this technique will be used in our course in normal gravity later. I wanted you to be aware of it. And there's no guarantee what the u should be. I mean, it may not be x squared, maybe something else. That's the art. You try something and see if it works. So that's the end of C6. I'll see you in the next class.